So we are back for, I believe this is part 4 of building a programming language. First of all, I just want to say thank you to all the new subscribers. This is pretty sick. And thank you for the kind comments. I will try to continue to improve my editing, but... Okay, hi, this is editing Maddie in the same outfit. So... I believe a lot of this video might be a little choppy and the audio may be desynced. I thought I had it figured out, but OBS is still giving me trouble on Mac, and I've recorded the entire video. And I don't want to re-record it because I'm trying to put out content. I apologize. I will get it figured out. And if you have any suggestions in the comments for software that can screen record on Mac that will not give me a bunch of problems, please comment. Thank you so much for watching. Like and subscribe. I'm so angry. Don't get your hopes up. I'm not a great editor, but I'm also not a great programmer. So that's why I'm doing this. So we're gonna learn today. Well, I am. You may already know this, but we're going to continue to parse through different expressions, possibly getting to evaluating them too, depending on how long it takes me to figure out. Parsing the rest of it. Where we left off last time was, I believe we had parsed binary expressions that are plus or addition, subtraction. So now we have to parse ones that are multiplication and division. That'll be a separate thing because they are higher precedence level. Remember, what was it? PEMDAS? Or is this? Yeah, it's PEMDAS. Dividing and multiplication is evaluated before adding and subtraction. So, to do that, I started looking at this before I started recording, but basically, all we have to do is currently, the term function, which is plus or minus, is calling the unary function, so it's going down the chain. So what we just need to do is, instead of calling the unary function, we have to call the factor function, because that is a lower precedence than unary, but higher than term. So now we have that. It's going to look remarkably similar to term. I actually did see in a separate book another way to do this where you don't have to have separate methods for term and factor by using basically just assigning precedence to different tokens. Maybe I will do that in a later revision, but for now we're just gonna follow what the crafting interpreters book is doing. So, alright, if the token is either a star or a slash, we know that it's multiplication, and we will go ahead and parse the inner part of that, return a binary. Fairly simple. And then let's see, what is next? So another thing that we need to worry about is different kinds of literals. So at the moment we're only checking for integers. We want to also check for other types of literal expressions. So literals would be either strings, numbers, true or false, nil, that kind of stuff. Oh god, I just remembered I did not add a special case for nil. So we're gonna head over to the token and allow, actually in my language it's gonna be called null. Just because in Swift it's called nil, and I don't want to get confused. So in my language, it'll be called null. So all we have to do to add another keyword is just add it to our dictionary. And then say null, boom. So next, I'm in the parser. So we are checking for, actually first, before we do that, we should test the multiplication division sign. So we do 10 divided by 5, 10 times 5. Let's see if we can get, if it correctly parses what we expect. So the next one after the 5 times 7 should be, so it'll be, the left will be integer value 10, right will be integer value 5. and then token will be a slash. Oops, what is going on? All right, and seam will be just a slash. Line, that will be 1, 2, 3, line 3. And then we will just go ahead and copy and paste that. And then for this one, it'll just be, I think I did the same thing. So plug seam will be the star, and then type will be star, line will be 4. So let's run these tests, see if they pass. Look at my Dragon Ball mug. They failed, but first look at my Dragon Ball Z mug. I got it from Target, along with a Dragon Ball Z beanie and 2 pairs of Dragon Ball Z socks. They're supposed to be Christmas stuff, but when you're an adult, Christmas is every day. Anyway, so let's see, what is the issue? Oh, that would make sense. So this should be 5, I think. Let's actually do this again. Test succeeded, boom. So that works. We do also want to test some more complicated expressions and make sure that we are evaluating things in the correct order, or at least creating the syntax tree in the correct order. So, for example, say we have something a little bit more complicated. So we have 10 plus 5 times 7. So in this case, normally we would just go from left to right, because binary operations, or just like adding, subtracting, multiplying, dividing, are what's called left associative, which means they move from the left to the right. So you say 10 plus 5 times 7. But because the multiplication is a higher precedence, we actually want to evaluate that first to get the correct answer. So you could actually, this would be equivalent. The parentheses make it easier to parse out what's in there. But if we say did this, now we evaluate 10 plus 5 first, because we know that parentheses have an even higher precedence than multiplication. So we want to actually check, I think a good test would be to do both of these, one with parentheses around the 10 plus 5 and one without. So these should be return 2 different structures. So this one should return the 10 plus 5 higher in the precedence. This one should return 5 times 7 higher in the precedence. So to test that, we are going to first of all have a binary. So for this one, the left side will be another binary, and that one will be 10 and 5, the token. I need like a shorthand to create a token. Actually, let's create a helper function, because I'm sick of typing this shit out. Token, we're gonna pass in a token type, and that's gonna return a token. So we're gonna say return, goddamn. I'm really bad at typing. I don't know if that's been evident. Token, and it'll be token type passed in. Theme will be token type. Raw value line will be, we have to pass that in. So now instead of typing that whole thing, we could just say token or get token. This saves a little bit of typing, not a whole lot, honestly, but better than having to do the. So it saves a little bit of typing at least. So that would be plus, and this one should be line 5. And then the right side will just be 7. Oh, and also these integer values. And then the token will be token star line fall. So, and we're just gonna copy and paste that. So for this one, though, instead the left side will be, let's actually just copy and paste that. So on this one, the right side will be 7 times 5. No, it'd be 5 times 7. Let's do star. And then this will be plus. And then this will be integer value 10. So I'm sure this looks a little bit confusing. So all we're doing is saying this for this more complicated expression. We're gonna say this is gonna be, the whole thing is gonna be the outer binary, which is this. And then the left side will be an inner binary. That will cause it to be evaluated first. So the inner binary will be a 10 plus 5. On the other one, the entire outer is 10 plus 5 plus 7. And then the right side is 5 times 7 because we want that to be evaluated first. So it's gonna fail because I forgot to update this. Oopsie. So we're getting an infinite loop. So let's just see why that is happening. So I think is because, why is this happening? Term is factor. So what do we do? Term, factor, binary, expression, comparison term. So I believe it is because, all done now. All right, let's see. We have our forgot to implement parentheses. So to do that, we have to check for a left parentheses and then evaluate or parse the expression in between, right after the left parentheses, and then consume a right parentheses. And then we're gonna just return the expression, I believe. So hopefully that fixes the issue. So no more infinite loop, which is nice. But we are getting an error, so let me run that again with the breakpoint. See, what is the previous token? Right paren, peak is a star. Let me look at the test, make sure I wrote things right. So it's right here that it's having the confusion. So token, so it's checking the right paren. I believe it should have been right. So, okay, I bet I know what's happening now. It is advancing when it evaluates the expression. So peak is, actually, I'm gonna set a breakpoint here and then rerun it. So after we evaluate this expression, so this is not actually where I want to be. There it is. Okay, yeah, let's run that again. So at this point, we're at the 5. So here, peak is equal to the right paren. So peak, right paren. So it seems like it should just advance and be fine at this point. But my guess is I'm stupid. So my issue, I think, was in the consume. I'm actually just calling advance and not actually returning the token that advance is returning. So it is falling through to this line, and that's why I'm getting an error when I shouldn't. So I'm actually gonna refactor this to be a guard, and then that way I know that it has to not fall through, because guards can't fall through. So instead, I'm just gonna go in the guard body. We're gonna throw that error, and here we're gonna return advance. I don't think consume actually even needs to return anything majority of the time, but that would be why my test was effing up before. So we're still failing, but I believe now should be more, yeah, it's not throwing that error anymore. So I think it's just failing because the code is wrong now, which is better. So, all right, let's debug that as well. Oh, so that actually makes sense. So I have to adjust my test. So here in the test, I'm actually assuming that both the right and the left will both be integers, and we don't actually want that, because it could be, now that we've changed the parsing code, the left could be an integer, could be a binary, and in the future could be any host of things. So we're gonna actually delete that whole thing. Here we're gonna say not as, we're gonna actually delete these expectations as well. So instead we're gonna say expect right, so test expression right dot Oh wait, we want to actually, go back. So Russian not left is, even go back anymore. So, all right. So we know that both of these are binary expressions. So left, right, boom. So we don't want them to be integers. So we're gonna do that. Now we don't need the guard because those aren't optional. We're gonna do this and this. So we're actually gonna put this outside of the guard. Gonna delete that guard statement. Gonna delete these casts. So now we have an expression. So these can be any expression. Think I wanna. So let's say you left expression. I don't know how to compare these correctly. So let me think for a second. I can't think of a cute way to do this. You know what? I'm just gonna say, I don't know what I'm gonna say. So my issue is, since these aren't concrete types, it's kind of hard to generalize the expectations to check if they're equal. Unfortunately, may need to pull these out into a separate test, but I don't really want to do that because it's gonna take a while and also make things less flexible. So what I'm doing here is, if everything's an integer, then we have those expectations. And then if, actually, you know what? I'm going to separate these into their own if statements though. So we're gonna say, I did this wrong. So we're saying if left is an integer and expected left is an integer, then we do this expectation. If right is integer, right, we do this expectation. And now we're gonna say if left equals best expectation as left, or dot left as a binary. Let's expected left equal expression dot left and binary first. So what I did here was, I check if the left is a binary and the expected left is a binary. If it is, we're gonna cast the left and right side of that first binary and the second binary into integers, and then check the value and check the type of the operator. This is not the most flexible way to do this, to be honest. And we're gonna have to fix this later when we have to parse other kinds of expressions. But for now, we're just gonna let this live. We're gonna copy and paste that, do right. I actually need to rename these things because I had the right value. So that's updated. See if the test pass. They do. Cool. So that means we're able to correctly parse things with different precedences. Let me see what else is in this chapter. So last thing we have to do is different types of literals. So we're gonna say if match say true, we have to match false. We have to match null, and we have to match string, and we have to match floats. So for each of these, we need to have something in the abstract syntax tree to represent each of these values. So this will be pretty straightforward. So first we have to have a Boolean expression, and that will just have a value that is a bool. We need a string value, will, you guessed it, be a string, and we need float. This could be a number of things as the representation, but I'm just gonna go for a double for this. I can't name it string. It's a reserved name, so there's a string val. And then lastly, we just need one for null, and that doesn't need a value. So now we have that. We just have to parse each of those for true. we're just gonna return boolean, the value of true, and for false, we're just gonna return a boolean with the value of false. For null, we're gonna return a null. For string, we're gonna return a string val, and then for the value, it will be previous tokens like seam, and then for float, we're gonna the token equal prev, and then we're gonna say do the same thing as an int guard let value equal double the tokens like seam, else we're gonna throw an error. I believe this should actually be previous that it's reporting the error on. And then we're just gonna return float the value of value. So that should cover all the literals we need for now. So let's make sure all our tests still pass. They do. And we're gonna add another test to test for other types of values. Do we have a test for parsing integers? No. So we're gonna say create a test, parse literal, let the source equal just a bunch of different literals. So we're gonna say 1.2 or 3 true, false, null, and then a string, say hello. Now we're gonna say hell yeah. So we have that. Now I'm just gonna copy and paste that code that creates the parser and parses it and returns a program. That is something I should probably put off in its own helper function. But will we? Maybe not. Being weird. So anyway, let's see. Next, we have to create the expected, what we expect to get in the functions. Expected expression, I believe we'll just, so we know these are all gonna be, well, actually we don't know what they are gonna be. So we're gonna say expected, we're just gonna have it be a bunch of general expressions. So expected, first one should be an integer with a value of 1. Second should be a float with a value of 1.3. Second should be a boolean with a value of true. Next one should be a boolean with the value of false. I think you know where I'm going here. Next one will be null. And lastly will be hell yeah. So that'd be a string val with the value of hell brother. Alright. So from there, we're just gonna loop through those expected things. First, we wanna make sure the count is right of the statement. So expect program statement.count should equal 1, 2, 3, 4, 5, 6. So it's gonna equal 7, including the end of file token. And then, wait a minute. Wait, no, this is the parser, so it's actually going to. We don't have to count in the file. I'm stupid because we're not scanning, we're parsing. So it's gonna be 6, and then from there we're gonna say for expression in expected, we're just gonna say if. Actually here, wait, no, never mind. Forget I said anything. All right, if let expected equal expression as integer, we're gonna say expect. Say let. Oh, also need to get the index, which I don't think I said this before. To do that in Swift, you just have to call enumerated on your array, and then there it will give you the index and object of that index. So we're gonna say let. Well, actually, we're gonna do that here. Let the test expression equal program or expression at I, or the statement at I. And then that statement would be, actually, let's force cast it to an expression statement. If I can spell that, expression, and this will be statement expression. So we have our expression here, and then we're gonna say test expression int equal test expression, and we're gonna force cast this in because we just want the test to fail or to crash if it's not what we expect, and that way it'll just stop running another test. So okay, so we have that. So we're just gonna say expectation expression I equals expression value. So cool. We're just gonna go ahead and repeat that for each one or each type. So we're gonna need float, booleans. So we're gonna need 1, 2, 3, 4 more. Alright, so let's do this one at a time. We're gonna cover float here. Cool, that'll be the same thing. Not string val. We're just gonna say this over here. Boolean. And then for this one, we don't actually have to cast it. So we're gonna run those tests. They succeed. We actually didn't need to, but we're getting a warning here because we actually just need to. We don't need to set expression anything. We just have to check that it is a null. If it's null, and if this is null, then we want test expression be null. So cool, we've passed all our tests. We are recognizing and parsing literals. I think I'm going to call it a video here. Next one, I believe we are gonna actually start evaluating some expressions. So stay tuned for that. And once we have evaluating done, we will have a complete interpreter, not complete, but at least a calculator, an interpreter that can do math. So next video, get ready to do some math. Thank you for watching. Please like and subscribe. Thanks again for all the new subscribers. Please keep it coming. I want to be famous. Anyway, thank you for watching. Bye.